Oh, hello everyone. Let's start off this video lecture by introducing one important concept, the concept of what is known as the control volume and the control surface. Before we do a mass and energy balance, it's always important you first define your control volume and the control surface, right? Excuse me. So what is a control volume? The control volume is any region in space which the fluid occupies. It can be an arbitrary region, and the surface that bounds the control surface is what is known as a control volume. The easiest example is the problems that you have solved quite a bit in mass and energy balance too, is when you have, say, liquid coming into a tank and then liquid going out, a continuous stirred tank reactor. And any volume in the tank, say the volume of the tank, can be considered as the control volume. And the surface that bounds this control volume is the control surface. Or when you consider flow through a pipe or a nozzle, any volume of fluid inside this nozzle can be a control volume, and the surface that bounds this volume is a control surface. Or a spherical tank, the volume inside the tank is a control volume. So first, before you solve any mass and energy balance problem, it is always important to first define a control volume, identify the control surface, and then go ahead and perform your mass and energy balances. And again, the control surface is important because the fluid can come into a control volume by cutting across the control surface. So keep that in mind. So the control volume can exchange mass, momentum, and energy across the boundaries. There is a flow of materials across the inlets and outlets of the control volume. There is a flow of heat can occur. And obviously, whenever you have a control volume and a control surface, there are going to be forces acting on the control volume and on the control surface. And these become very important, say, when you do your momentum balance. And of course, whenever you have system, work can be done on the system by the surroundings, or the system can do work on the surroundings, right? And the sign convention for work is also going to be very important when you do the energy balance. Okay, so let's go ahead and define our statements, for the mass and the energy balance. So I would strongly recommend that you do this every time you solve a problem. It doesn't take long at all. So first, please clearly write out the statement of your mass and energy balances. So for conservation of mass, we have the net rate of mass leaving the control volume plus rate of accumulation of mass within the control volume is equal to the rate of generation of mass in a control volume. So if there is no reactions going on, say, in a system, then this term is 0. And this is what normally you have been dealing with, where you're simply stating the conservation of mass is the net rate of mass leaving the control volume plus rate of accumulation of mass inside the control volume is 0 if there is no chemical reactions occurring in the system. The conservation of energy, the net rate at which energy leaves the control volume plus rate of accumulation of energy inside the control volume is equal to Q dot minus W dot, where Q dot is the rate of addition of heat to the control volume from its surroundings, and W dot is the rate of work done by the control volume on its surroundings. So, and usually when you have the work W dot is usually composed of multiple terms. The two common, the ones that you have dealt with in MEB2 are the flow work and the shaft work. And it's very important to keep in mind the sign conventions for Q dot and W dot when you, depending on the kind of the energy balance that you write down. So please, why I'm saying this is if you go to a different course such as thermodynamics, the sign convention is going to be different. So that is why you have to pay close attention to how you define your energy balance, or the statement of your energy balance. In this statement, we say the net rate at which energy leaves plus accumulation of energy is equal to Q dot minus W dot. So the sign conventions for Q dot and W dot are going to be very important. So please pay very close attention to that. Right? Okay. So, and we will get to that in a few minutes towards the end of the, once we start doing the energy balance. Okay, so let's go on to the mass balance first. Let's keep it simple. Let's say this is the tank. Fluid comes in at a flow rate m1 dot, fluid goes out at a flow rate m2 dot, mass flow rate. The mass of fluid in the tank is m tank. Let's assume no reactions take place in the control volume. The control volume is basically the volume of the tank. So mass comes in, mass leaves. So the mass balance states the net rate at which mass leaves plus rate of accumulation of mass inside the tank is equal to 0. So the rate at which mass leaves is m2 dot, the rate at which mass comes in is m1 dot. This is the net rate at which mass leaves, plus what do you mean by accumulation is how the mass inside the tank is changing with time, right? That is accumulation. Accumulation means something is changing with time. And that something is the mass of the fluid inside the tank. Remember, you're always doing a mass balance on the fluid inside the tank, right? So m2 dot minus m1 dot plus d by dt of m tank is 0. So it's very simple. That's your mass balance. And again, this is just to illustrate sometimes how do you calculate the mass flow rate. Mass flow rate is nothing but the density times area times velocity, right? At section 2, which is the exit. So when you take the density times area times velocity, that's your mass flow rate. And again, density times volume is mass, and how that is changing with time is your accumulation term. So the mass balance is pretty simple. I think this simple mass balance can be used to solve first two problems in homework 1. And we will use this actually quite a bit more in this course as we move along. Okay, so let's go on to the energy balance. Again, the statement is very important. The net rate at which energy leaves the control volume plus accumulation of energy in the control volume is equal to Q dot minus W dot. Again, please memorize the statement, write this down. How you define your energy balance, the statement is extremely important. And the sign conventions for Q dot and W dot are also extremely important, right? And the sign conventions depend on the statement of the energy balance, right? So let's first look at this work term W dot. W dot is the rate at which the system does work on the surroundings. So what are the two kinds of common work terms? This is directly from your mass and energy balance book. There are two types of commonly encountered work terms. This is the shaft work and that's the flow work. The shaft work or the rate of work done by the process fluid on a moving part within the system. For example, a pump rotor, right? So when you have a pump rotor, then the surroundings does work on the system, and according to our sign convention, it is going to be negative. So the other common work term that you encounter is what is known as the flow work. The flow work is the rate of work done by the fluid at the system outlet minus the rate of work done on the fluid at the system inlet. To better explain this, right? What happens, say this is the tube which contains fluid. Now flow comes in and tries to enter the tube. At the inlet, the surrounding has to do work on the system for the fluid to come in. It has to push this liquid away from the surface as that it comes in, right? So at the inlet, the surroundings does work on the system. Now consider the exit, right? Now when you consider the exit of the tube, the system has to push this liquid which is close to the exit away such that it can go out. So at the exit, say section 2, the system does work on the surroundings. Alright? I hope that is clear. So that is why the net rate at which work is done by the system is at the exit minus that at the inlet, right? Because at the exit, the system does work on the surroundings, while at the inlet, the surroundings does work on the system. So the net flow work is nothing but pressure times your volumetric flow rate. Think about this. What is rate at which work is being done? Rate at which work is being done is nothing but pressure times area, which is force. Area times velocity is rate of doing work, right? While area times velocity is nothing but your volumetric flow rate V dot. So the net rate at which the flow work is nothing but P out times V dot out minus P in times V dot in. And again, so this is very important. The sign convention for work is if the system does work on the surroundings, the sign convention is positive. While if the surroundings does work on the system, then the sign convention is negative, right? So please keep this in mind. This is going to be very important. So your flow work is nothing but P2 times V2 dot minus P1 times V1 dot, where V dot is your volumetric flow rate, which is nothing but the area times velocity. Again, the sign convention is Ws dot okay. So, but before we do that, it's useful to know this mathematical manipulation where your flow work is again P2 times V2 dot minus P1 times V1 dot. All I've done here is multiplied and divided by the density. So now density times area times velocity is nothing but your mass flow rate. So it is nothing but m2 dot times p2 over rho minus m1 dot times p1 over rho. Just simple mathematical manipulation. And 1 over rho is your V cap, right? Which is nothing but rho is your density kg per meter cubed, and 1 over rho is nothing but meter cube per kg, or your V cap. Just keep this in mind, just simple mathematical manipulation, because you know why we want to do this is finally we want to get to the term U plus PV cap is nothing but H cap, right? So that is why we want to get it in terms of V cap. So that's your flow work. Shaft work, again, which can be done by pumps, turbines, or you have a stirrer in a system. You pump in energy, right? So you want to stir your contents of your reactor. Shaft work is positive. The system does work on the surroundings. Say, for example, if you have a turbine. And negative if the surroundings does work on the system, pumps, stirrers, and so on and so forth. You're going to encounter this quite a lot in a number of problems. So Q dot, again, the sign convention for Q dot is going to be very important. It's positive if heat comes into the system, and negative if system gives out heat, right? So again, keep this in mind. This is also going to be very important when you solve problems. If you get the sign convention wrong, then all your numbers are going to be wrong, right? So please pay attention to detail and to the sign convention, depending on how you define your energy balance. Okay, so let's keep moving on. So what we have done so far is the net rate at which energy leaves plus the accumulation of energy is equal to Q dot minus W dot. We got the sign conventions for Q dot and W dot. And we saw that the work term consists of two terms, usually the flow work and the shaft work, right? Now let's go in and see how we can work on the left hand side of the energy balance, right? So let's do that. So this is the key thing. Flowing streams carry energy, right? Now let's say you have a stream that has a mass flow rate m dot. This fluid carries energy with it. And usually, how do you characterize that energy? Usually the book uses the terminology E cap. The E cap is the energy per unit mass of the flowing fluid. Energy per unit mass is nothing but joules per kg. So what are the terms that comprise this energy per unit mass? You have the internal energy per unit mass, which is U cap. And you have the kinetic energy per unit mass, which is V squared over 2. And you have the potential energy per unit mass, which is nothing but G times Z. So any flowing fluid contains these three terms, right? And now, now we are ready to go ahead and do the energy balance using this concept. So again, let's just consider the simplest case. You say you have a tank. Fluid comes in, fluid goes out. Fluid comes in at section 1, fluid goes out at section 2. The mass inside the tank is, say, m tank. So the energy balance says that the net rate at which energy leaves plus accumulation of energy inside the control volume is equal to Q dot minus W dot. So what is the net rate at which energy leaves? It's nothing but your mass flow rate times energy per unit mass at section 2 minus the mass flow rate times energy per unit mass at section 1, right? Very simple. Nothing complicated here. So putting in the terms, that's nothing but m dot times the energy per unit mass consists of the internal energy, kinetic energy per unit mass, and potential energy per unit mass at section 2 minus that at section 1. Very simple. Now, what is the accumulation term? The accumulation term is nothing but how the energy inside the tank is changing with time. Like say in homework 1, in the final problem where the oil inside the tank was getting heated. Obviously, when the oil inside the tank is getting heated, the internal energy is probably changing, right? It gets more and more hot. And as a result of which the internal energy inside the tank is changing with time. So d by dt, how things is changing with time, the mass of the fluid in the tank times energy per unit mass gives you the energy inside the tank, and how that is changing with time is your accumulation, right? So d by dt of mass inside the tank times internal energy, kinetic energy, and potential energy per unit mass. In most of the cases, this term is going to be negligible compared to your internal energy per unit mass. Say in homework 1, in problem 3, when the oil inside the tank is getting heated, obviously the internal energy is increasing because your temperature inside the tank is increasing, right? So that's why this term comes into play, or there is accumulation of energy inside the tank. So again, as you can see, it's very straightforward. So please just pause, write down the energy balance and evaluate the different terms. The net rate at which energy leaves the control volume plus rate at which the energy inside the control volume is changing with time, or the accumulation term, is equal to Q dot minus W dot, right? This is the rate at which energy leaves. There is the rate at which energy comes in. This is the rate of accumulation of energy inside the control volume, and this is equal to Q dot minus W dot. Simplest case, steady state, nothing changes with time. So d by dt of the energy inside the tank is 0 because say the temperature is constant. So then one term vanishes. So the net rate at which energy leaves is equal to Q dot minus W dot. Rate at which energy leaves, rate at which energy comes in, is Q dot. This is your flow work, and this is your shaft work, right? The work term consists of two terms, flow work and shaft work. Now you can rearrange the terms. You can take the flow work to the left hand side. When you take the flow work to the left hand side, as you can see, you get the same expression that you have in mass and energy balance too, right? So basically all you do is when you take the U cap and add that to PV cap, that's nothing but H cap, right? So very simple mathematical manipulation. Take the flow work to the left hand side, add your U cap to the PV cap, that gets you H cap, right? And this is a standard expression that you have seen and in MEB too. And again, this the other big assumption that you have here is if it is steady state, then m1 dot equal to m2 dot equal to m dot. So the mass flow rate is a constant right throughout the system, and this is your final expression, right? Delta H cap plus half delta V square plus G delta Z is Q dot minus WS dot over M dot. So please, this is very simple mathematical expression. You should be able to derive this expression. So please spend some time in going through this derivation and make sure you can get to this final expression. Again, the sign conventions for Q dot and WS dot are going to be important. You're going to be using this formula in a number of problems. But please don't blindly memorize this formula. There are going to be a number of instances where you might have to start off from the basic definition of the energy balance and work out what formula you're going to use. Be very careful. Say a common example, like say, this is what is known as a splitter nozzle. Fluid comes in, there's one inlet, but now there are two outlets, right? So what do you mean by delta H cap or half delta V square? So it doesn't make much sense in blindly using this formula for this particular problem, right? So you need to pause, start out from the definition of the energy balance. The net rate at which energy leaves plus rate of accumulation of energy equal to Q dot minus W dot. I keep repeating this again and again because please don't go looking for formulas. Be comfortable with the definition of the energy balance and the sign convention and use that as a starting point for a lot of problems, right? And we will solve a lot of problems in this class in the energy balance. Again, please derive this energy balance on your own. You should be able to do this closed book.